In the early hours of June 2nd, Mount Etna erupted with a towering burst of ash, searing gas and fragmented rock, sending a massive plume high into the Sicilian sky. The plume stretched for several kilometers, a dramatic display from Europe's most active volcano. Despite the scale of the eruption, there were no reports of injuries or property damage, and air travel to and from the island experienced minimal disruption. Eruptions from Mount Etna are typically categorized as Strombolian, marked by regular bursts of lava and ash, but this event may fall outside that usual classification. Mount Etna's most recent activity began with a surge in internal pressure as hot gases accumulated beneath its surface. This build-up eventually caused part of a summit crater to collapse, opening the pathway for a violent release. From this breach erupted a pyroclastic flow, a searing cloud of ash, toxic gases and volcanic debris that raced down the slopes at breathtaking speed. Shortly after, rivers of molten lava spilled from the crater, branching into 3 separate paths as they descended the mountainside. As the lava cooled and hardened, Italy's National Institute of Geophysics and Volcanology declared the eruption officially over by Monday evening. Though dramatic, such events are not unusual for Mount Etna, one of the most persistently active volcanoes on the planet. Volcanic eruptions vary greatly in intensity, and scientists classify them based on how explosive they are. At the gentler end of this spectrum are Hawaiian eruptions, characterized by slow, steady lava flows that advance calmly down volcanic flanks. These events, while destructive to anything in their path, usually impact a limited area. In contrast, the most violent eruptions, known as PLINIAN eruptions, launch ash, gas and pulverized rock skyward with such force that the plume can reach the stratosphere. The catastrophic eruption of Mount Vesuvius in 79 AD is one infamous example, immortalized by Roman accounts and the ash-entombed ruins of Pompeii and Herculaneum. When such a towering eruption column collapses, it can blanket vast regions in fiery debris, leaving devastation in its wake. Strombolian eruptions occupy a middle ground. Named after the Italian volcano Stromboli, these eruptions are relatively mild and occur with rhythmic regularity. Explosions from Strombolian events send glowing fragments of rock and cinder tens to hundreds of meters into the air, usually without posing widespread danger. However, Etna's latest eruption proved more forceful than a typical Strombolian event, suggesting a level of explosiveness beyond that category. Anticipating when a volcano will erupt remains a complex challenge, much like forecasting the weather. Scientists have made significant advances in recent decades, but precise predictions remain elusive. Instead, volcanologists rely on indirect indicators to understand what's happening deep within a volcano. As magma rises toward the surface, it fractures surrounding rock, triggering swarms of small earthquakes. By analyzing seismic patterns, experts can track this movement from the Earth's depths. At the same time, the ground around a volcano may subtly swell due to the pressure of incoming magma. Changes so minute, they require satellite monitoring to detect. Some volcanoes also emit gas continuously, even outside of active eruptions. By analyzing the composition of these emissions, scientists can detect shifts that suggest fresh magma is nearing the surface. But having data is only part of the equation. To interpret what this information truly means for the future, volcanologists must also understand the unique behavioral history of each volcano, its patterns, tendencies and quirks, like a personality shaped by geologic time. Many people today believe that volcanic eruptions are occurring more frequently than in the past, but this perception doesn't hold up under scientific scrutiny. The apparent increase in volcanic activity is largely a result of significant advancements in global monitoring systems and the rapid spread of information through modern media. With real-time satellite data, seismic networks, and a 24/7 news cycle, eruptions that once might have gone unnoticed are now recorded, broadcast, and even live-streamed to the world. High-risk regions such as Italy, the United States, Indonesia, and New Zealand benefit from a sophisticated volcanic surveillance, which includes tools like GPS, gas sensors, and thermal imaging. These technologies allow scientists to detect the subtle warning signs of an impending eruption, such as ground deformation, gas emissions, or seismic tremors, well before magma reaches the surface. This early detection is crucial not only for safeguarding lives, but also for helping local authorities deliver timely alerts and evacuation orders. For those visiting or living near volcanoes, paying close attention to these official warnings can mean the difference between a breathtaking experience and a life-threatening disaster. Volcanologists have long debated whether this massive basaltic volcano is capable of producing a PLINIAN eruption, and if so, what the technical mechanisms behind such a transition would be. PLINIAN eruptions are among the most powerful and destructive volcanic events on Earth. Named after Pliny the Younger, who documented the catastrophic eruption of Mount Vesuvius in 79 AD, these eruptions are defined by towering columns of ash and gas that can penetrate deep into the stratosphere, often exceeding 20 kilometers in height. They are driven by the explosive release of volatiles, primarily water vapor, carbon dioxide and sulfur dioxide, trapped within viscous, silica-rich magma such as rhyolite or dacite. The viscosity of this magma prevents gases from escaping easily, allowing enormous pressure to build up within the magma chamber. When that pressure is suddenly released, it generates an eruption of extraordinary violence. Etna's usual activity, in contrast, is fed by basaltic magma that is low in silica and viscosity. This fluid nature allows gases to escape more easily, leading to more effusive or mildly explosive Strombolian eruptions. The magma is also relatively gas-poor compared to the volatile rich magmas that drive Plinian activity. Because of this, Etna is often perceived as less likely to generate a Plinian eruption. However, this perception overlooks the complexity of the volcano's internal plumbing and geologic history. Despite its tendency for moderate eruptions, Mount Etna has produced powerful explosive eruptions in the past. One of the most notable events occurred in 122 BC, when an eruption ejected large quantities of ash and pumice that devastated the nearby city of Catania. Ashfall was so severe that it reportedly caused the collapse of buildings, and Roman authorities granted tax relief to the affected region. Geological evidence suggests that this eruption reached the stratosphere and had characteristics consistent with sub-Plinian or even borderline Plinian behavior. This event demonstrates that under certain conditions, Etna is capable of far more explosive activity than is typically observed today. To understand how Etna could produce a future Plinian eruption, we must consider several key mechanisms. First is magma evolution. Over time, magma stored within the volcano's plumbing system can undergo fractional crystallization, a process that removes early forming crystals and enriches the remaining melt in silica. This more evolved magma becomes more viscous and can trap volatiles more effectively, increasing the potential for an explosive eruption. Second is the accumulation of volatiles. Even basaltic magmas can become gas-rich if stored under high pressure in the crust. If the release of this gas is delayed by a blockage or a viscous cap near the surface, it can lead to a sudden catastrophic decompression. Third is conduit obstruction. If the central vent becomes sealed off by solidified lava or altered rock, the magma below can build up pressure. A breach in this sealed conduit could trigger a massive explosive release. Lastly, tectonic activity could play a role. Etna sits near the boundary of the African and Eurasian plates, a region prone to earthquakes and crustal deformation. A seismic event or sudden structural shift could destabilize the magma chamber and initiate a rapid eruption sequence. While these conditions are rare, they are not impossible. Etna's magma system is highly dynamic, with evidence of magma mixing, deep and shallow reservoirs, and periodic injections of more primitive magma from depth. Such complexity means that even if Plinian eruptions are not common, the potential exists under specific circumstances. Should a true Plinian eruption occur at Mount Etna, the consequences would be dire. A towering eruption column would inject vast quantities of ash into the atmosphere, disrupting air traffic across southern Europe and the Mediterranean. Tephra fallout could bury towns and farmland for dozens of kilometers around the volcano, including the city of Catania. Pyroclastic flows, though less common in basaltic systems, could threaten nearby communities if the eruption involves more evolved magma. Ash inhalation, infrastructure collapse, and widespread agricultural damage would create a humanitarian crisis, especially given the population density around the volcano. To understand what could trigger such an eruption at Etna, we must analyze the internal magmatic plumbing system, gas content, magma composition, and tectonic influences in the region. Mount Etna is an open-vent basaltic stratovolcano situated on the convergent boundary where the African plate subducts beneath the Eurasian plate. Most of Etna's eruptions are classified as Strombolian or effusive, meaning they involve moderate explosions or lava flows with low viscosity basaltic magma. These eruptions are facilitated by the relatively easy degassing of the basaltic magma due to its low silica content, which prevents excessive pressure buildup. However, under certain circumstances, this dynamic can change dramatically. The most critical factor in triggering a PLINIAN eruption is the accumulation of highly viscous, gas-rich magma at shallow depths within the volcanic conduit system. This type of magma typically has a higher silica content than basalt, such as andesite, dacite, or even rhyolite. For Etna to produce such magma, fractional crystallization and magma mixing must occur over an extended period in a relatively closed magmatic chamber. In this scenario, basaltic magma injected from the mantle undergoes slow cooling and chemical evolution, increasing its silica content. Alternatively, injection of hot basaltic magma into a reservoir of more evolved silicic magma can remobilize and mix the magmas, dramatically increasing gas content and temperature, both of which heighten the explosive potential. Another key element is the inability of the ascending magma to degas efficiently. In an open vent system like Etna, gas is typically released steadily, which prevents large pressure buildups. However, if the conduit becomes temporarily blocked due to crystallization, collapse, or plugging from earlier lava flows, the trapped volatiles, including water vapor, carbon dioxide, and sulfur dioxide, can accumulate to critical pressures. The deeper the magma is stored before ascent, the more volatiles it can retain. Once the pressure of these gases exceeds the strength of the overlying rock, an explosive decompression event may occur. This sudden release of gas can fragment the magma into ash and pumice, propelling the eruption column tens of kilometers into the atmosphere, a defining trait of a PLINIAN event. Tectonic activity also plays a crucial role. Seismic swarms or fault movements around Etna could destabilize the magmatic system by facilitating rapid magma ascent, or creating fractures that change pressure regimes within the volcanic edifice. A sudden injection of fresh basaltic magma from depth, accompanied by volatile enrichment, could also push the system past its threshold. Additionally, the structural complexity of Etna, including its multiple summit craters and flank vents, means that a shift in vent location or collapse of a crater wall could instantaneously change the dynamics of an eruption. Importantly, scientists cannot predict precise recurrence intervals for rare events like PLINIAN eruptions at any volcano, including Etna. These events depend on complex, non-linear interactions within the magma chamber, conduit system, and external tectonic environment. What geologists can do is monitor for signs that the volcano is transitioning from its current relatively passive behavior to one that may support larger, more violent eruptions. These signs would include significant changes in magma chemistry toward higher silica content, elevated levels of gas emissions, especially CO2 and SO2, increased seismicity, unusual ground deformation, or long periods of dormancy that could allow gas-rich magma to accumulate undisturbed. Today, Etna is one of the best monitored volcanoes in the world, with a network of seismometers, gas sensors, GPS stations, and satellite surveillance. These systems are capable of detecting the warning signs of a major shift in eruptive behavior, such as increased seismicity, ground deformation, changes in gas emissions, and signs of more evolved magma. While there is currently no indication that Etna is preparing for a PLINIAN event, the volcano's complex geologic history reminds us that its potential should never be underestimated. The most powerful PLINIAN eruptions in history stand as some of the most dramatic and destructive natural events ever recorded. These rare events have left lasting scars on landscapes, civilizations, and even the global climate. Among them, the eruption of Mount Vesuvius in 1709 CE is perhaps the most iconic. This event buried the Roman cities of Pompeii, Herculaneum and Stabiae under several meters of ash and pumice. Eyewitness accounts, especially from Pliny the Younger, describe a colossal umbrella-shaped eruption column estimated to have reached about 33 kilometers high. The intense heat and suffocating ash killed thousands in moments. The volcanic material preserved buildings, food, and even human remains in extraordinary detail, offering a haunting snapshot of ancient Roman life frozen in time. In 1815, Mount Tambora in Indonesia unleashed the most powerful volcanic eruption in recorded history. The eruption began on April 5th and climaxed on April 10th, with a violent explosion that reduced the mountain's height by more than 1,500 meters, forming a vast caldera. It ejected roughly 160 cubic kilometers of material and is classified as a VEI-7 eruption, the highest on the Volcanic Explosivity Index, just below the theoretical maximum of VEI-8. The eruption column may have soared over 40 kilometers into the stratosphere, injecting vast amounts of sulfur dioxide that circled the globe and dimmed sunlight. This triggered a dramatic drop in global temperatures and led to the year without a summer in 1816. Snow fell in June in New England, crops failed across Europe, and widespread famine followed. More than 71,000 people died, many from starvation and disease in the aftermath. The 1883 eruption of Krakatoa, also in Indonesia, is among the most infamous volcanic disasters in history. Following months of unrest, Krakatoa erupted with cataclysmic force on August 27th. 4 enormous explosions were heard up to 3,000 miles away, and the final blast was so powerful that it ruptured the eardrums of people over 40 miles distant. The eruption destroyed 2/3 of the island and created a caldera that later gave birth to the currently active Anak Krakatoa. The eruption column likely reached 27 to 30 kilometers high. The explosion generated tsunamis up to 40 meters tall, which devastated nearby coastlines and killed over 36,000 people. Global temperatures dropped by more than 1.2 degrees Celsius, and sunsets around the world were painted vivid red due to the volcanic aerosols suspended in the atmosphere. In the Philippines, Mount Pinatubo erupted violently on June 15, 1991, after more than 500 years of dormancy. The eruption ejected about 10 cubic kilometers of tephra and produced a 35-kilometer high eruption column. Its ash cloud spread across Southeast Asia, reaching as far as Africa within 2 weeks. The eruption was preceded by accurate warnings from volcanologists, which allowed the evacuation of tens of thousands of people and significantly reduced the death toll. Still, the eruption caused more than 800 deaths, mostly from roof collapses under the weight of wet ash. The massive injection of sulfur dioxide into the stratosphere created a global haze, reducing sunlight and cooling the Earth's surface by up to 0.6 degrees Celsius over the next 2 years. It was the second largest eruption of the 20th century in terms of material ejected. Even larger in volume, though less well known, was the 1912 eruption of Novarupta in Alaska. It was the most powerful eruption of the 20th century, discharging over 30 cubic kilometers of ash and pumice. Despite its remote location, the ashfall was felt hundreds of kilometers away, and it blanketed what became known as the Valley of 10,000 Smokes, a region filled with thousands of fumaroles venting steam from the ash deposits. Novarupta's eruption column likely exceeded 30 kilometers, and the eruption's effects were global, including atmospheric dust that altered weather patterns temporarily. The scale of the eruption far exceeded nearby Mount Katmai, which collapsed due to the draining of magma beneath it, though Katmai was originally thought to be the source of the eruption. Mount St. Helens in Washington state erupted on May 18, 1980, after 2 months of increasing seismicity and visible deformation of the volcano's north flank. The eruption began with a massive landslide, the largest in recorded history, which uncorked the pressurized magma and triggered a lateral blast that devastated an area of nearly 600 square kilometers. The vertical PLINIAN phase that followed sent a column 24 kilometers high into the atmosphere. The eruption killed 57 people, destroyed 250 homes, and drastically reshaped the landscape. Although relatively modest in volume compared to other Plinian events, its combination of lateral and vertical explosive forces makes it one of the most studied eruptions in modern volcanology. In 1600, Huaynaputina in southern Peru erupted with such force that it became the largest historical eruption in South America. The Plinian column soared high into the atmosphere, and pyroclastic flows buried villages and agricultural land. The eruption disrupted the Inca population and sent volcanic aerosols into the stratosphere, leading to widespread crop failures. Tree ring data and ice cores suggest it contributed to one of the coldest decades of the Little Ice Age. Reports of famine and societal unrest as far away as Russia have been linked to the climatic effects of this eruption. Roughly 7,700 years ago, the eruption of Mount Mazama in what is now Oregon created the massive caldera that holds Crater Lake. This prehistoric Plinian eruption expelled about 50 cubic kilometers of material in an explosive event that ejected ash across much of the northwestern United States. The eruption column likely rose over 30 kilometers high. The mountain lost much of its summit, forming a deep basin that later filled with rainwater and snowmelt, becoming one of the most pristine lakes in the world. The eruption had lasting effects on Native American communities and ecosystems across the region. One of the most extreme eruptions in the last 5,000 years occurred around 1,800 years ago at the Taupo volcano in New Zealand. This event was so violent that it blasted more than 100 cubic kilometers of pumice and ash into the air. The eruption column may have reached over 50 kilometers high, the highest plume ever estimated from a volcanic eruption. The eruption darkened skies across the central North Island, buried the landscape under thick pyroclastic flows, and is recorded in oral traditions of the Maori people. Tephra from the eruption is used as a geological time marker across much of New Zealand. Finally, the eruption of Thera, now known as Santorini, occurred around 1600 BCE and was one of the largest volcanic events of the ancient world. It destroyed the centre of the island, created a large caldera, and likely triggered massive tsunamis that affected Minoan settlements on nearby Crete. The eruption's exact volume is debated, but it likely exceeded 40 cubic kilometers of material. The eruption column is estimated to have reached 30 to 35 kilometers high. Ash layers from Thera have been found in deep-sea cores and across the eastern Mediterranean. Some researchers suggest this eruption contributed to the collapse of the Minoan civilization and possibly inspired the legend of Atlantis. It caused climate anomalies, crop failures, and may have had cascading effects across multiple Bronze Age societies. These Plinian eruptions, though rare, show the immense power that volcanoes can unleash under the right conditions. They remind us that while such events may occur only once every few centuries or millennia, their impacts can be immediate, far-reaching, and catastrophic, influencing human history, reshaping geography, and altering climate on a global scale. If you found this video informative, don't forget to leave a like, share it with others who need to know, and subscribe for more eye-opening updates from the world of science and nature. Stay curious, stay safe, and we'll see you in the next video.